Hi, Dr. Rajiv. This video is used to present our physics laboratory report, which is the T3 Joule-Thomson effect. And in this group, we have three persons, which is the first one is me, Chang Ming Wei, second is Xi Shuyan, and third one is Wang Wei Xiang. So we will present about the part by part. So the first part will be the objective and apparatus. The objective of this experiment is used to demonstrate the principle of gas cooling by expansion. The second one is to demonstrate the thawing process. And the third one is to demonstrate the Joule-Thomson principle. So the apparatus we use in this experiment are the first one is Joule-Thomson apparatus. The second is temperature probes and digital meter. And the third one is carbon dioxide and nitrogen gas supply.
For my part, I will talk about the analysis. This is the data for the carbon dioxide. So, based on the graph, we can see that as the pressure increase, the temperature also increase. For this experiment, we will gonna use least square method to find the more accurate result. So this is the first part of the least square method. So the gradient we find out using this equation is 0.5892 degrees Celsius per bar, and then the intersection point is 0.10857 degrees Celsius. This is the second part of the least square method. So for the uncertainty for the gradient, we obtain 0.04 degrees Celsius per bar. Thus, our gradient we obtain is 0.59 plus minus 0.04 degrees Celsius per bar for carbon dioxide. So we go to the intersection point. So the uncertainty we get is 0.02 degrees Celsius. As a result, we obtain intersection point of 0.11 plus minus 0.02 degrees Celsius. This is the data for the nitrogen gas. So as we look at the graph, so as the pressure increase, the temperature also increase. Okay, so for nitrogen gas, we will doing the same step as the carbon dioxide we do before. So we will use least square method to find more accurate result. So the gradient we find here is 0.289 degrees Celsius per bar, and then the intersection point will be negative 0.0378 degrees Celsius. So this is the second part of the least square method for nitrogen gas. So as a result, we found out that the gradient for the nitrogen gas is 0.29 plus minus 0.02 degrees Celsius per bar. And then as for the intersection point, we will obtain negative 0.04 plus minus 0.01 degrees Celsius. Since this experiment we do we do with two different type of gas, which is carbon dioxide and nitrogen gas, so we will do comparison between these two. So we look to the graph. The blue line represents the carbon dioxide and the orange line represents the nitrogen gas. We found out that the carbon dioxide has steeper slope compared to the nitrogen gas. So why the graph of carbon dioxide has higher slope compared to nitrogen gas? So this is because carbon dioxide has stronger quadrupole moment, larger molecule and larger electron clouds, leads to greater polarizability compared to the nitrogen gas. So therefore, CO2 has stronger intermolecular attraction than nitrogen gas causes the greater cooling effect for the expansion compared to nitrogen gas. For this part, we will find the Joule-Thomson coefficient where the symbol used is mu. So the equation to find the coefficient is mu equals to 2a over RT minus B over Cp, where A and B is the constant of gas. R represents the universal gas constant. Cp is the specific heat of gas at constant pressure. And lastly, the T is represents the temperature. So at temperature 299 Kelvin, the coefficient obtained for the carbon dioxide is 7.79 times 10 to the power of negative 6 Kelvin per Pascal. While for the nitrogen, while for the coefficient for nitrogen is equals to 3.76 times 10 to the power of negative 6 Kelvin per Pascal. So this value obtained will be our theoretical value. Since we obtained the value of Joule-Thomson coefficient for experimental and theoretical values for carbon dioxide and nitrogen gas, so we will find the percentage difference between it. So for the carbon dioxide, the experimental value obtained is 5.9 times 10 to the power of negative 6, and the theoretical value obtained is 7.79 times 10 to the power of negative 6, and then the percentage difference obtained is 24.262%. Whereas for the nitrogen gas, the experimental value obtained is 2.9 times 10 to the power of negative 6, and the theoretical value obtained is 3.76 times 10 to the power of negative 6. So the percentage value between it is 22.872%.
For the discussion of this experiment, we have found out that the Joule-Thomson coefficient for CO2 is higher than nitrogen gas. The percentage error for carbon dioxide is 24.3%, while for nitrogen gas is 22.9%. These errors shows that the experiment is considered a success as they are not high. Both of the values are positive, hence they are real gases, and the temperature will decrease during the gas expansion through the throttling point as there's experienced pressure decrease. The throttling process is actually an isentropic and irreversible process in which there is no work done and heat transfer in or out of the system. The throttling of the flow causes a significant reduction in pressure of the gas due to the local pressure losses caused by the porous plug in the Joule-Thomson apparatus. Next, the ideal gas will actually have 0 degrees Celsius per bar coefficient due to the Joule-Thomson effect is isentropic, which is constant enthalpy, since H equals to internal energy plus pressure times volume, which is also equals to internal energy plus NR temperature. The temperature of either gas will remain constant, so it is not real gas, unlike our result found in this experiment. The coefficient for carbon dioxide is higher than nitrogen due to its stronger intermolecular force compared to nitrogen gas, as it is stronger quadruple moments, larger molecule, and also larger electron cloud, which will lead to greater polarizability compared to the nitrogen gas. Hence, the carbon dioxide has a larger cooling effect from throttling process compared to nitrogen gas. So for this experiment, we are able to demonstrate the principle of gas cooling by expansion via the throttling process, which follows the Joule-Thomson principle, which has satisfied all three objectives of this experiment. The Joule-Thomson coefficient for the carbon dioxide is 0.59 plus minus 0.04 degrees Celsius per bar, and for the nitrogen gas, 0.29 plus minus 0.02 degrees Celsius per bar, respectively. And that's all from us for this Joe Thomson effect experiment. Thank you.